so that this diagram commutes, which means that composition of G with I1 is equal to J1 and composition of G with I2 is equal to J2. So this is the definition of co-product in a category. So let's see another example. Let's see what are co-products in the category of left OR modules. So co-products in OR mod. Remember that in our previous session we discussed products in category of left OR modules. In fact, we discussed product of two modules because it is easy to see the product of two objects. Product of an indexed family of objects is slightly more complicated, not very complicated. So in order to begin with the understanding of concept of product and co-product, it is advisable to try to understand the product of two objects. So we are going to discuss product of two left OR modules in the category OR mod. So let's see this construction. So let R be a ring with identity, because you know that whenever we talk about OR modules, the ring R is always a ring with identity. Identity means multiplicative identity. So let R be a ring with identity. And capital M and capital N, as we did in case of product of two modules, we are going to use symbols M and N for left OR modules. So and M and N be left OR modules. Be left OR modules. Then we know that we have done this thing when we were discussing the product of two left OR modules in our previous session. We know that Cartesian product of M and N, M cross N, this is set of order pairs XY such that X belongs to M and Y belongs to N. And we know that this Cartesian product is also a left OR module under component-wise operations, is also a left OR module under component-wise operations. So under component wise operations, we have discussed this in detail in our previous session. So we claim that it may look a little strange to you. In our previous session, we have proved that M cross N is product of M and N in the category of R modules. Now we are going to prove that the same object M cross N is co-product as well. We are going to prove that the same object is co-product as well. Let me repeat it. In our previous session, we have proved that M cross N is product in the category of left OR modules. Now we are going to prove that the same object M cross N is also co-product in the category of left OR modules. We will simply change the symbol. It is the same object, but when we will discuss this object as co-product, we will use symbol of addition instead of this cross. Anyway, let's continue our discussion. So we claim that the same object M cross N is also co-product. This is product. We have proved that already, and we claim that this is also co-product. It is also co-product of M and N in the category of left OR modules or mod. So this is what we claim. However, when we discuss M cross N as co-product, the symbol we use is M plus N instead of M cross N. So in considering this particular object M cross N as co-product, we write it as M plus N. But you must note that M plus N, as far as left OR module is concerned, this is same as M cross N as left OR module. Its elements are order is XY such that X belongs to M and Y belongs to N, and operations are component wise. However, when we consider it as co-product, we write it as M plus N. So here let me tell you what injections are. Here injections are given by, when we talk about co-product, we talk about injections. Here injections are given by so let's see what injections are. M plus N is the co-product of M and N. This is what, in fact, we have to prove that. I'm simply using this phrase co-product. We will establish that this is a co-product. So injections have to be from M to M plus N and from N to M plus N, as we have discussed in case of sets. So we are going to denote it by I1 and we will denote it by I2. So let's see how these injections are going to be defined. Suppose X is an element of M, then I1 will take it to elements of M plus N are ordered pairs. So X will go to X 0 order pair. X belongs to M and 0 belongs to N. And about I2, suppose we are given an element Y of N. This injection I2 will take Y to this particular order pair 0Y. 0 belongs to M and Y belongs to N. Let me write it clearly. That is, effect of I1 on X is equal to this order pair X0, and effect of I2 on Y is equal to this order pair 0Y. So this is the way we define I1 and I2. So we claim that the same thing M cross N is also co-product. We write it as M plus N. Anyway, we shall prove that with I1 and I2 as defined above, M plus N becomes co-product in the category of left OR modules or mod. So this is what we are going to prove. So let's see how proof works. So in order to prove that M plus N is co-product, we will consider a diagram in the category of left OR module. This is the diagram we will consider. I will just write it. So we shall prove that if this is a diagram, C is a left OR module, and from M and N there are these maps, call them J1 and J2. So if this is a diagram, in the category of left OR modules, this is the way we represent it, then there exists a unique module homomorphism from M plus N to C, a unique module homomorphism from M plus N to C, such that and you know that what we are going to do, we have M plus N and we have injections from M to M plus N I1 as defined above, and from N to M plus N I2 as defined above. And if there is a diagram C and we have maps from M to C, and this is map J1, and N to C, and this is map J2, then there exists a unique homomorphism from M plus N into C. Let's call it G. So then there exists a unique homomorphism from M plus N into C, we denote it by G, such that this diagram commutes. And what do we mean by this? Is that we mean that G composed with I1 is equal to J1, and G composed with I2 is equal to J2. Let's name it 1. This is also 1 anyway. So this is what we have to prove. So let's see how does proof go. First of all, we have to define this particular map G. This is map from M plus N into C. First we will define this map, then we will come to commutativity, and then we will come to uniqueness. So we have to do 3 steps. First of all, we have to define this map G, then we have to prove that this diagram commutes, and then we have to prove that G is unique. So let's define the map G. So first of all, we define effect of G on an element of M plus N. Remember that elements of M plus N are just ordered pairs, X, Y, such that X belongs to M and Y belongs to N, just order pairs. So we define Gxy is equal to, now just note how we define this map. X belongs to M, so this X belongs to M. J1 is going to effect on X, and we will receive an element J1X in C. Similarly, this Y belongs to N, and J2 will effect on Y, and we will receive an element in C. So J1X will be in C, J2Y will be in C. Since C is a module, we can add these 2 elements in C. So this is what I am saying. Effect of G on this order pair XY is equal to effect of J1 on X, then effect of J2 on Y. J1X is element of C, J2Y is element of C. C is a module, and module is basically an abelian group. So these 2 elements can be added. So this is the way we define this map C. and this can be very easily proved that this is a module homomorphism. When we study category theory, then we don't go for these minute details. So which is module homomorphism? So which is module homomorphism? So this is the way we define G. So our first task was to define G, and next we have to see that the diagram commutes. Secondly, to see that G circle I1 is equal to J1, we consider. Let me show you. The diagram commutes means G circle I1 is equal to J1. We have to prove that. Similarly, we have to prove that as well. So, to see that G circle I1 is equal to J1, consider we see effect of G circle I1 on X, and this is equal to effect of G on I1X. This is how we define composition effect, and this is equal to, now let me show you how we defined I1. I1X is X0, this order pair. I1X is equal to this order pair whose first element is X, second element is 0. So I1X is equal to GX0. Now effect of G is effect of J on first element plus effect of J1 on first element and effect of J2 on second element. So G effected upon X0 will give us J1 effected on X plus J2 affected on 0. This is our definition, in fact. This is our definition. So this is equal to this. And this is equal to, and we know that it is J1X, and since J2 is module homomorphism, so J2 0 will be equal to 0, and therefore G composed with I1 effected upon X is equal to J1 affected upon X, because J1 X plus 0 is equal to J1X, and therefore G circle I1 is equal to J1, because effect of G circle I1 on any X is equal to effect of J1 on that particular X. So G circle I1 is same thing as J1, and similarly we can prove that. We have done one of these two, we have done one of these two, this one, this can be done similarly. So similarly we can prove that. Similarly we can prove that G circle I2 is equal to J2, and having done that, we have concluded that the diagram commutes. Therefore the diagram we have called the diagram 1, therefore diagram 1 commutes. And thirdly, we have to establish that G is unique. So uniqueness of G. So in order to establish uniqueness, we take another module homomorphism from M plus N to C, so that this diagram commutes, and we will prove that module homomorphism is equal to G. So we take H will become equal to G. So let M plus N into C, let's call it H, be a module homomorphism such that all we have to do is we have to draw the same diagram. Instead of G, we have to use H. So such that same diagram, H instead of G. So such that M plus N, these are injections from M to M plus N, and then from N to M plus N, I1 and I2, and this is another diagram. M to C we denoted it by J1, and then from N to C we denoted it by J2. And suppose that there is a module homomorphism from M plus N into C, and we denote it by H, such that this diagram commutes. And by saying that this diagram commutes, we mean that H composed with I1 is equal to J1, and H composed with I2 is equal to J2. So we have chosen a module homomorphism H such that this diagram commutes. We shall prove that H is same thing as G. So we shall prove that H is equal to G. So we shall prove that H is equal to G. So let's see the proof. Now for any x belonging to M, x belonging to the left are module M, effect of this thing that H circle, H composed with I1 is equal to J1, means that effect of H circle I1 on X is equal to effect of J1 on X, because these two morphisms or maps are same, so their effect on X will be same. So this means that H of I1X is equal to J1X, and this means that H of I1x, we have already seen that effect of I1 on x is equal to this order pair x0, and this is equal to j1x, and this implies that h of effect of h on x0 is equal to effect of j1 on x. And note that if we add 0 here, it will not make any difference because 0 is additive identity in the left or module, and this implies that effect of h on x0 is equal to j1x, and if you like you can write 0 as j20, effect of j2 on 0. Effect of j2 on 0 will be equal to 0 because j2 is module homomorphism, and module homomorphism preserves additive identity. So j20 is equal to 0, and this implies that h effect of h on x0 is equal to j1x plus j20 is exactly what g of x effect of g on x0 is. Remember that this is the way we have defined gxy is equal to j1x plus j2y. So j1x plus j20 is equal to gx0 because of this particular definition. So hx0 is equal to gx0. Similarly, we can prove that effect of h on 0y is equal to effect of g on 0y. So having done that, now we see what is effect of h on. So far we have seen effect of h on x0 and effect of h on 0y. Now we will see effect of h on a general element of m plus n. So let's do that. Now effect of h on xy, this is general element of m plus n. M plus n is just the Cartesian product of m and n. So hxy is equal to, this is equal to effect of h on, now m plus n is a module, and you can write xy order pair as x0 order pair plus 0y order pair, because addition of m plus n, under addition of m plus n, x0 order pair plus 0y order pair is equal to xy order pair. So you can write this as this. Since h is module homomorphism, so this is equal to h effected upon x0 plus h effected upon 0y, because module homomorphisms preserve addition, and this is equal to hx0 is equal to gx0 and h0y is equal to g0y. Since G is module homomorphism, so this can be written as gx0 plus 0y, and adding these two, this is equal to gxy. So effect of h on xy is same as effect of g on xy. Therefore h is equal to g, and therefore G is unique. So we have completed all the steps. Therefore, M plus N is co-product of M and N in the category of left OR modules. So therefore, M plus N is co-product of M and N in the category of left OR modules. So we have completed this proof. We defined co-product of two objects, and so far we have worked with co-product of two objects only. We can define co-product of a family of objects as well. So let me give you that definition. So definition: let C be a category then co-product, then the co-product of a family of objects. Let's take that family of objects. This is family of objects A lambda, such that lambda belongs to this capital lambda. In fact, we are using lambda as indexing family, because if we use I, then we have used I for injection as well, so it will make things slightly, if we use I, then things will get mixed up. So I have decided to use lambda as indexing set. It does not make any difference. So then the co-product of a family of objects A lambda, such that lambda belong to lambda. Lambda is the indexing set, and these are elements of this indexing set in the category C is an object Now again, note about the symbols. We used the symbol plus when we wrote co-product of two objects. We used plus. But for a family of indexed family of objects, the symbol we will use is this one. The same symbol, similar symbol which we use for disjoint union. So this is co-product of this indexed family of objects. So this is the indexing. Lambda belongs to capital lambda and A lambda. So this is the way we write the co-product of a family of indexed family of objects. So is an object this in the category C such that, so we have two conditions. First of all, this particular object is equipped with maps from A lambda to this co-product, and we denote it by I lambda for this object. If there is other object, then this will be indexed by that particular object. So is equipped with maps. These are called injections. And these maps are in the category C. And secondly, and if there is a map from A lambda to an object C, let's denote it by J lambda, where lambda belongs to lambda. And if this is a diagram, in the category C, then there exists unique morphism or unique map from this co-product lambda belonging to lambda, A lambda to C, and let's denote it by G, such that this diagram commutes. This is co-product, and this is injection, I lambda. And if there is an object C and a map from A lambda to C, we denote it by J lambda. For each lambda there is a map. Then there is a unique map from this co-product to C, we denote it by G. And this is going to happen for each lambda. Commutes for each lambda belonging to lambda. That is, what does commutativity mean? We know that commutativity means that G composed with I lambda is equal to J lambda. This is for every lambda belonging to lambda. So this is definition for co-product of an indexed family of objects in a category C. It looks slightly complicated, but if you try to understand it with the help of co-product of two objects, you will be able to make it. Let me comment that it is not necessary that in every category products or co-products exist. It may happen that product exist. It may happen that products do not exist. Same is the case with co-products. But what we have done is we have defined product and co-product in a category if they exist in that particular category. So